Hi, my name is Emily Diana, and I'm talking about our paper Multiaccurate Proxies for Downstream Fairness. This is joint work with Wesley, Gill, Michael Kearns, Krishnaram, Kenthapadi, Aaron Roth, and Saeed Sharifi-Malvajerdi. So algorithmic fairness has been featured quite prominently in the news recently. We've seen issues with gender discrimination in resume filtering, with some racial discrimination in parole decisions, and also some nasty cycles of predictive policing, causing kind of disadvantaged neighborhoods to be targeted more and more. So in this paper, we asked the question, what if we want to train a model that is fair with respect to a sensitive feature that's been redacted from the training data? So this could be for legal or policy reasons, that the feature that we would like to optimize for in respect to fairness of race or gender isn't in the data. So how can we make a model fair with respect to something like race if we don't have data about race? So we take a pipeline approach. We consider a space with non-sensitive features, labels, and then a sensitive feature Z. We have a proxy learner and a downstream learner. The proxy learner will take in the sensitive feature Z and the non-sensitive features X and Y, make a function that then the downstream learner can use to impute values of Z. And this downstream learner is the one that is then generating the fair machine learning model to do things such as filter resumes. And we have a specific statistical model class that the proxy will be drawn from, and a specific model class that the downstream learner will be using. And the overall goal is for the proxy learner to find a proxy Z hat, such that if a downstream learner trains a model H that is fair with respect to Z hat, H is also fair with respect to Z. Now, our key insight here is that the proxy can be real valued. So normally when we write fairness constraints, they're defined with respect to a binary valued group membership. But we instead write these fairness constraints with respect to a real valued group membership. And this is simply done by taking a conditional probability, such as the probability of a mistake, given that someone is in group K, and rewriting it as the ratio of two expectations. And note that once we have these expectations, we can plug in real values here. So if this ratio with Z is the same as this ratio with Z hat, then if a model is fair with respect to Z hat, it is also fair with respect to Z. We can use this to come up with a proxy definition, which basically says that we have an alpha proxy if those two ratios are within some absolute value alpha of each other. And then with that, we can write a linear program that allows us to solve for a proxy, a fair proxy. So we encode these multi-accurate, so these constraints are multi-accuracy constraints. If we want Z hat to be an unbiased estimator for Z on the set of points where H errs. So they'll draw the constraints, and then we can optionally choose an objective. So I'll show us some experiments. We compare the use of our proxy, either the just kind of basic proxy or one where we add an MSE objective, so MSE objective not required, to the true labels and a logistic regression that is a baseline proxy. And here's a plot showing that if we train a model to be fair with respect to the true labels, then that Pareto dominates the other situations. Next best is our trained proxy model, where we just aim to satisfy the multi-accuracy constraints. And then the baseline proxy, the one where we have mean squared error is after that. And then finally, the baseline proxy. So from this, we see that it's possible to efficiently train proxies that can stand in for missing sensitive features to effectively train downstream classifiers subject to a variety of demographic fairness constraints. And I just want to note that these results crucially depend on the assumption that the data the proxy learner uses is distributed identically to the data that the downstream learner uses. Thank you very much, and I would love for you to contact me with any questions.